chemistry, reactions in general tend to center around the movement of electrons. So David, absolutely, acids, bases, we're going to touch upon that and how they are going to be a big part of a lot of the reactions that we're going to see today. And yeah, so there's a lot of parallel structure in there for sure. Bulky reagents, Nikki, yeah, absolutely. Whether, you've got stereoselectivity going on, whether it's going to be impeding the reaction, whether it's going to be actually helpful itself. Yeah, absolutely. So good. Now, if I were to tell you, like the key fundamental principle behind reactions themselves, it's going to be something that's you're going to be like, well, duh, I get that, Ari, but I cannot stress how important this understanding is. Like, in order for a reaction to happen, wow, my pen. Okay, in order for a reaction to happen, what must be true about the product compared to the reactant? In order for a reaction to happen, what must be true about the product compared to the reactants in the reaction? What do you think? And this is going to be true, and all of the reaction conditions, the type of players that you have will all center around this key idea. What do you think? What might I be referring to about the product compared to the reactants itself, regardless of what kind of reaction, like in Gen Chem or in, Orgo itself, it has to be stable. All of the reaction conditions are going to favor the reaction that happens that's going to create the more stable product. Exactly. So yeah, it's going to be happy on its own. Right? So if you understand that one fundamental principle, all of the things that we're going to talk about in this session are going to be in that scope. So all about the stability of the products, whether it's acid-base, whether it's nucleophilic, whether it's, so in a redox reaction, all of that is on the same thing. So David, a lot of that can come from it, right? So exergonic, meaning that it is going to be a spontaneous process. But why is it spontaneous? It's because the product is going to be more stable than the reactants itself. Exothermic just means it produces heat through the process of reaction. Most exothermic reactions are going to be exergonic, but not always. You just want to be a little bit careful about that. But yeah, it's got patterns. And I think this was something I struggled with a lot when I was in school. When I did organic chemistry, I did really, really bad because the majority of my time I spent on memorizing specific reactions. I did not spend any time understanding that there are trends and patterns, that you can predict how reactions happen if you understand what the players are. So that's why we're going to spend the large part of today focusing on the players. For you to be able to pinpoint what the players are will give you the powers to predict the products of these reactions. Now, the good thing about Orgo on the MCAT is that it's very limited in scope, right? We're talking about organic chemistry, meaning that they can only really center around like carbon and oxygen and hydrogen. So it limits the kind of reactions that you have. But secondly, they will generally be biologically in context, right? So biochemistry is usually how Orgo is tested. And, if you have our Kaplan books, I would say the first 5 chapters of that Kaplan, the biochem Kaplan book, are going to be ChemPhys specific, and a lot of that is going to be centered in the application of organic chemistry within a biological context. And that's going to be about a quarter of the ChemPhys section. So a quarter of one section is going to be organic chemistry focused, usually in the context of biochem, which means that there is not a limitless amount of reactions that you need. It's very limited in scope. So as long as you understand these key patterns and trends, you can be able to do this on your own practice on the MCAT itself. So it's going to be good news, really, really good news. Okay. So here is a kind of a scary series of reactions. We're going to see this slide actually again and again. But Patrick a little bit earlier mentioned things like electrophiles and nucleophiles. So that's really what we're going to focus on in the first part of this is, how do we know that's a nucleophile? How do we know this is an electrophile? How do we understand that that's going to be a solvent? What kind of solvent is it? And how do we know that this weird alien looking thing is going to be taking off and leaving? And why would we even have that occur? So let's talk a little bit about these individual players themselves. So I want to know from you all, what is a nucleophile? What are characteristics of nucleophiles? It's kind of important. I agree, Patrick. What do you think? What are nucleophiles? What is a characteristic of a nucleophile then? You can even break down the words. I'm a huge fan. I don't know if you've had a chance to talk to John Linick in the chat in any of these sessions, but he talks a lot about word roots. Word roots are like a magic secret. It's a secret that if you understand the secret, that you have the powers to understand what terms mean, even if you've never heard of them before. So what do you think? Nucleophile. John is also a nomad. I've learned that about him. It's funny that he was on your couch, Patrick. Could be a base. Yeah, we will talk about that. Absolutely. Electron donors. Very nice. You're right. Why do they donate electrons? Tara's right as well. They tend to be very strongly electronegative. So the word nucleo refers to the nucleus of an atom, and the charge in the nucleus of the atom is generally going to be full of protons. So it's going to be positively charged. Phile means to love or to like. So it likes positive charge. It itself is generally going to be negatively charged. So it's going to donate electrons to make some bonds. It is nucleus loving. So these are all really important characteristics to understand. So in your organic chemistry history, tell me, like, what are some good examples of a nucleophile? What are some examples of nucleophiles that you can think of right now, or you've seen before in some reactions? Nucleophiles, so things that are nucleus loving. Patrick's a nucleophile? Possibly. That lingo does start. A lot of like Latin root words, so important. What are some examples of nucleophiles like you can think of? I've got a whole list. This entire page is going to be full with nucleophiles, but I want to give you a chance to kind of recall that first. Cyanide, David, very nice. So cyanide's a really good one, and the fact that it's an anion is the kicker. So it's got a negative charge. Good. Hydroxides, also a really good. Amines, so the nitrogen in the amino acids and how that is going to be used to catalyze, not catalyze, but form the peptide bond itself. Yeah, that's another great nucleophile. So here are some examples. Here's our cyanide anion here. We got our bromine, we got our hydroxide. These are all characteristics of good nucleophiles because they have a full negative charge on them. So the more localized or more like stronger of a negative charge you have, the better the nucleophile is going to be in general. We've also got some examples of these atoms, not necessarily what I would normally think of as a nucleophile, but the reason why these are nucleophiles technically is because of the pi bonds, right? So we've got our, localized electron density between these atoms because there was like a double and a triple bond. Now, tell me about the likelihood of this acting as a nucleophile. What do you guys all think? And this is like another secret to the majority of the answers in organic chemistry. Why would I say, nah, I don't know if it's necessarily going to happen that often that I've got what looks like benzene. Why wouldn't I usually think of benzene as a good nucleophile? What do you think? Because remember, the key to reactions happening is that they are not happy where they are. If the reactant can turn into something else and it's stable, then it's going to do it. But what about this particular benzene is not likely to actually react? I mean, you can under certain conditions. It's just not all that likely. If you were thinking, I don't know, like resonance, resonance being the key, the answer to all organic chemistry problems, then you'd be right. This doesn't have a localized double bond. It doesn't just sit in that one position. Yeah, it's so stable. Absolutely. David and Nikki and Guest 7525, you're right. This is stable on its own. This is distributed. This is like a partial, bond throughout this entire molecule itself. So anytime you have those electrons that are distributed over the whole molecule, it's a terrible nucleophile. Yeah, delocalization, resonance, you got it. And then here we've got some of our more likely nucleophiles. So we mentioned the amine at the end of an amino acid. We got, technically water. Lone pairs is really what we're going for here. So lone pairs can act as a nucleophile. Okay, so yeah. Now the other idea here is this statement. I feel like this statement is in my own head. It's the statement that my professors would say. I'd be like, oh, good. Yeah, I got to write that down. I'll write it down. Good bases are good nucleophiles, but good nucleophiles are not good bases. And so I'd write that down. I'd have it memorized. It's kind of like my definition of enantiomers, non-superimposable mirror images. I can recite that, but I don't fully understand what that always means. And I think it's worth kind of spending a bit of time on understanding exactly why this statement is true, because this is kind of confusing. Why is one not the same as the other? So I'm going to draw a little diagram, very fancy one. Actually, I realize that I can't do that because I might be drawing over my face. 1 second. Okay. Okay, let's consider this. If I have a big circle, and this is going to encompass all of my nucleophiles. Okay, so let's take, for instance, the bromine. What do you know about bromine as a base? Actually, let me do that. It's okay. If you can't see what I'm drawing, that's interesting. I'm gonna have to verify with Patrick, not just you. Oh no. I did erase it for a second. So Patrick and Henry are gonna have to verify for me. You need to, oh, you don't need the slides. You don't see the slides? There's no slides? Have I been pointing at things and you guys haven't been seeing it? Okay. Oh my gosh. Can you guys all see what I'm talking about now? Oh Lordy. Okay, my bad. Can you see now? Thanks for letting me know, like earlier rather than later. You just see me. Okay, give it a second. You should be able to see it soon. Okay, no, that was my bad. I forgot to share my screen initially. Okay, now you should see slides. Do you see slides? There, okay. I had an entire set of statements. There we go. No, don't apologize, David. Thank you for letting me know. Man, that would be terrible. Good thing I only got to one slide. Okay, there we go. So my drawing is a very fancy circle here, and I've got the words nucleophile in it, and I've got a bromine anion. I want you guys all to tell me about base. What is a good base? What is your definition of a good base? What is your definition of a good base? The bromine. The buddy, he's a friend, but he's also really chill on his own, which is a good clue here. What do you think? What is a good base? Or your definition of something that would be characteristic of a good base? Oh, we'll talk about his like clingy friend fluorine in a bit. Yeah, it's a proton acceptor. It is, so really good base is also very happy on its own. I think maybe that's worthwhile describing. A good base is happy on its own. Happy on its own. So wait, actually, maybe I'm going to retract my statement. 1 second. I think that's confusing the way I phrased that. A good base is going to be a proton acceptor. I think we'll work with that. Proton acceptor. And this is what kind of acid-base definition? When we're talking about movements of protons, proton acceptor, proton donator, like what kind of type of base is that? I'm thinking about like, that's okay, Tara. Yeah, like let's describe like what I mean by good and bad, David. This is why I'm going to want to spend a little bit of time here. They do. Patrick is absolutely right. They tend to be similar. And I want to make sure that we have a good distinction between these two. So I'm thinking like Bronsted-Lowry style. So a Bronsted base is the one that we would want to call, that's right. And we'll talk about the Lewis acids and bases in just a bit, David, because that's actually a really important key point. So yeah, Bronsted base is going to be a proton acceptor. A good base is going to be a proton acceptor. What do you think about bromine? What do you think about this guy? Bromine as a base. Is bromine, the bromine anion, a good base? It's got a nice solid negative charge. You'd think that it'd want to have a proton around it, but is this a good base? it's more like an umbrella, David. Like electrons are the broadest term, and then we can get a little bit more specific and talk about bromines. Yeah, and so Patrick's got it. Bromine's kind of happy on its own. It is happy on its own. This is actually the conjugate base of a really strong acid. Hydrobromic acid, bromic acid is going to be, or hydrogen bromide, or HBr, is going to be a really strong acid. But a strong acid means it wants to give off this proton, okay? So this is like not really a fan of grabbing another proton. So this is my definition here. Nucleophiles are anything that's going to attack, you know, something. It's going to donate electrons, okay? So anything that has a good set of electrons and it wants to share it or give it away is going to be a good nucleophile. But not all good nucleophiles are good bases. This is a really good example. Bromine is a good example. Iodine's another good example. But good bases are a subset. These are the ones that will want to pick up a proton, but all good nucleophiles are going to be good bases. All good bases are going to be nucleophiles, but not all good nucleophiles are going to be good bases because of this distinction. So the reason why I drew it like this is to show you that bases are just a subset of nucleophiles, okay? So bases are a subset of nucleophiles. They're the ones that will want to donate electrons, and generally speaking, this is going to be specific to protons. So bases, so donate to proton, whereas a nucleophile is going to donate to anything, but in the context of organic chemistry with the MCAT, it's mostly going to be a carbon, okay? Yeah, so this is a key idea, is to help you understand that the difference between that statement, good bases are good nucleophiles, but not all good nucleophiles are good bases, is to understand that bases are just a subset of a nucleophile, specific for protons, whereas not all nucleophiles are going to want to grab a proton because some of them are just happy on their own. They've got an electron and they've got a negative charge, but they don't always just want to grab another proton. Sometimes they're just happy to be there, okay? Okay, let's move on to our next player. We talked about nucleophiles and how they really are full of electrons. The other side of this story is going to be our electrophiles. So electrophiles, breaking down the word again, they like electrons, they like negative charge. So in the context of organic chemistry, biochemistry application, what is like the primo electrophile? Like, what is the one electrophile that you're going to want to see and pay attention and immediately think, oh, that's an electrophile when you see it? What do you think? What would be a really good example of an electrophile that every time you see it, I want you to think electrophile? That's going to be my site of attack. Exactly, Tara. Great synopsis. And I want you to think the other half of that peptide bond chemistry that we talked about. David, exactly, that's right. So carbonyl carbon is really a great electrophile. And let's talk about why exactly that is. It wants to accept, the more positive it is, the better that electrophile is going to be. Here is an excellent electrophile. This, in fact, this is like the best electrophile you're possibly going to have, is a carbocation. It's got a full positive charge here, versus a bromomethane. Tell me which of these two, carbocation or bromomethane, is going to be the better electrophile. And better electrophile means it is, generally speaking, not going to be very happy as it is. It wants to react with something and form a more stable product. So the more unstable your reactant is, the more likely this reaction is going to happen, the stronger the electrophile is going to be. So between a carbocation, we're going to talk a lot more about carbocations later on, and bromomethane, what do you think is going to be the better electrophile between these two? Carbocations are interesting. Yeah, they are. I mean, would you normally expect to see a full positive charge on a carbon? No, not really. This is a very unstable reaction. So if you consider these two carbons, the one that's going to be the better electrophile is going to be the carbocation. Also, and I'm going to mention this a little bit more better, what is the likelihood of this, like a methyl group losing its proton and forming this particular kind of carbocation? What do you think is the likelihood of this ever appearing? You might be taking clues from the way I'm phrasing that question. But yeah, I'm kind of nudging you in the right direction. Should a methyl group really ever form this? A carbon and all of its supporting is just a bunch of hydrogens around it. This is just like a precursor to our discussion that we're going to have at the end of the session today about SN1, SN2. Yeah, it's not going to happen. This is not ever. This is like literally never going to happen. Why? Because it has no buddies to give it some support. So yeah, so don't worry about this kind of carbocation. We'll talk about other more likely carbocations, but in general, this is not something that's favored as a reaction. And we'll talk about its place in the nucleophilic reactions in a little bit. So here we've got a couple other ones. We've got acetone, isopropanol. Between acetone and isopropanol, I think this is actually a better question here. Which one's the better electrophile? Acetone, isopropanol. And the way you can spot good electrophiles has to do with molecular dipoles. We might be like divulging a little bit into the gen chem realm here, but molecular dipoles will dictate this type of partial positive charge. So which one's the better one? Is it acetone or isopropanol? Which one has the stronger molecular dipole? In other words, which one has more electron density being pulled away from the central carbon, going towards something that is more electronegative? So think about like what's surrounding that carbon. So this acetone carbon has a double bond to an oxygen. Oxygen is being more electronegative here. And then I've got isopropanol, and it's got a hydroxy group. Acetone is the correct answer. Acetone is more, a partially positively charged. It's going to be the better electrophile between those two. So you guys are absolutely correct. Right, so think about the pi electrons that exist over here. It's going to pull more electron density away, so it's going to be a slightly better electrophile. Carbonyl carbons, like I said a little bit earlier, is really the center of the majority of the reactions. So I want you to be on the lookout for this kind of functionality, and whatever else the carbon's going to be attached to is going to dictate the kind of reactivity you're going to have. We do discuss this in a different session a little bit more. But just as a preface, you'll just want to keep that in mind, okay? Reactivity of electrophiles. Okay, we have another set of players, our leaving group, and kind of continuing the theme that we described about how reactions happen. What are characteristics of a good leaving group? What makes a leaving group good or likely to leave, I guess? What are characteristics of good leaving groups? So remember, the product is going to be what compared to the reactants? What are characteristics of good leaving groups? So leaving groups are essentially just functional groups that take off, right? So what would be good for a molecule could be size, possibly. Nikki, if you want to elaborate a little bit more on that, what about the size allows for it to be a happy leaving group? Exactly, that's right, stability, right? Remember I told you a little bit earlier, all of this is going to be centered around the stability of the product itself. So if I have a nucleophile that's going to grab the electrons after the bond is broken and it's happy to do that, like the bromine, right? So here bromine takes off. Those are all great ones. Yeah, so resonance, we'll get to that one. Actually, David, you anticipated what I was going to say. It is about stability. Why are esters, inorganic esters like phosphate and nitrate, why are those going to be good leaving groups? What do you think? Great anticipation. Anything that's going to make it more stable. So whether it's like a halogen, like the chloride, bromide, iodide, whether it's going to be the inorganic esters. What about those inorganic esters makes them good leaving groups? Yeah, stability. They're resonating, right? This negative, this like double bond doesn't sit here. Sometimes it goes over here. Sometimes it goes over here, over here. Same deal with these guys. All of them will resonate, and therefore it spreads out that negative charge, and it's happy to have it on its own. So stability on its own is exactly why. So 787, you're right. Another good example. So here we've got alcohols, water, esters or ethers. Those are not esters. So ethers, alcohols, waters are all good examples of leaving groups, especially if I can like protonate something and then it kind of comes on. So here are another good examples here. Our final ones are these ginormous molecules. So tosylates, mesylates are another good example. Often these are added so that it will allow for a functional group to come off a lot more easily than it would normally on its own. Okay. So yeah, so tosylates and mesylates, similar to inorganic esters, are stable because it has the ability to resonate and distribute that negative charge across the entire molecule. So here, okay? So if leaving groups that are good are the ones that are stable after leaving, then you can probably predict that bad leaving groups are just not stable. So for instance, what makes, as it is, what makes this thing right here a bad leaving group? What do you think? Actually, so what actually, maybe the better question is, what is the product? If this guy takes off, the nucleophile takes off, what is the product of here? So this is an ether. So it's carbon, oxygen, carbon. What makes this a bad leaving group? Or what is the leaving group after it leaves? So if I follow this reaction around, my nucleophile is going to attack that carbonyl, that carbon that's attached to the oxygen, right? It's a methoxy, exactly. Nice nomenclature, David. So alkoxide, hydroxides, terrible leaving groups. These are all like really strong bases, right? So things that are like strong bases generally don't really want to take off on their own. What could I do to these actually? It's kind of, it's a hint to what we saw a little bit earlier. So the reason why it wouldn't just be a carbocation, Tara, is because we've got a nucleophile here. So let me see. Oh, it doesn't actually do it. But like if this like was to attack it, this would take off, and then this would be the product over here, like that guy, right? So it wouldn't be just a carbocation on its own. It would be because I've got a nucleophile attacking at the same time, so I don't get the carbocation. We'll get to the carbocation in a bit. Yeah, either adds a hydrogen. The nucleophile is generally going to be the inducer of the movement of the electrons here, though. So yeah, hydroxides, alkoxides, if I added a hydrogen, if I were to protonate it, if I had it in acidic conditions like Nikki is describing, I would be able to create a great leaving group and be fine. Yeah, you guys are absolutely correct. Nice work. How about like this? If I've just got an alkyl group, alkyl just meaning a bunch of carbons around, this is not going to take off. Why? Because the product of this is horrible. It's going to be something that is not going to occur. So see how that nucleophile just doesn't do anything? Yeah. So carbanions, a negative charge on a carbon. Carbons don't really like to hold charges at all. So whether it's negative or positive, it doesn't really want to do it. Hydrides, horrible. Like a hydrogen would never just take off regardless of how strong that nucleophile is. So hydrides are also terrible leaving groups. So I think the key here is the more reactions that you get a chance to experience and understand, the more these kinds of patterns, you never really just see these kinds of products, you know, in the course of any of the reactions that you do. The reason why is because they just don't happen. The products are too unstable. Okay, so that's the little spiel on leaving groups. Yeah, so I think now would be a great time to do a practice question. So let's do this. I'm going to give you a minute. There's a poll. It's on the second tab next to the chat. What I want you to do is take a minute and take a look at this question and pull in for your results, and then we'll discuss it together. So take a minute and do question 1 on your own. Okay, welcome back, everyone. So the question is asking which of the following is the best leaving group. So characteristics of really good leaving group has to be that they're happy on their own. And it looks like the majority of us are pulling in for the correct answer here. So let's take a look. Characteristics of good leaving groups, happy on their own. Weak bases are good leaving groups. Out of the 4 results here, the only one that is technically a weak, in fact, it would be more like an inert base, is answer choice D. So iodine, chloride, bromine, all good, leaving groups. They're all stable on their own. Let's talk a little bit about this guy. It is technically also a halogen, but what makes fluoride a terrible leaving group? And David, I'm trying to even recall what that is, which kind of tells you something. That it's probably not all that likely to be tested on the MCAT, so I probably wouldn't worry too much about it. What do you think? Why is fluorine not a good leaving group? What about fluorine is kind of like the exception to a lot of the rules that we have about halogens? I'll give you a little like helpful hint regarding the reactivity of this particular atom. Yeah, Nikki, that's a great thing. Yeah, it's a weak acid. Yeah, electronegativity, its size. And the reason why is because it's got like so many electrons in its valence shell, but it's tiny. This is fluoride. And whereas like iodine is huge and it's got the same number of electrons in its valence shell. So the fact that it's much bigger but accommodates the same number of electrons means that this guy is like pretty happy to have one more electrons to fill its octet, but it's not, you know, it can accommodate that extra one. So yeah, it could be a part of the bulk, like the iodine is bigger so that it can like hold that electron a little bit better. But fluorine, because it really kind of does want to fill its octet, but look at how crowded those electrons are in that valence shell. It is extremely electronegative, but also not happy. It doesn't really want to be on its own. So Nikki's got a really good point. Out of the halogens, only fluoride is going to be the weak acid. Weak acid meaning it doesn't really want to give up its proton. You guys all, I've heard this like multiple times, and I swear I've seen Wedding Crashers, but I can't quite recall the scene. But in Wedding Crashers, they talk about the stage 5 clinger. Fluorine is a stage 5 clinger. It doesn't really want to let go of really anything. If you see a fluorine on a compound, it's not going to come off. It's not going to be kicked off. It's not going to do anything. It's going to hold on to its proton, and that's it. Because it's so clingy. It just really wants to hold on to stuff and won't let it go. So you want to keep that in mind, that you're never really going to see a fluorine, not never, but like unlikely to see a fluorine on its own. It's going to want to hold on to something. It is a good movie. I remember laughing a lot. I just don't remember that exact scene, but in any case. Okay, let's take a look at another one. So again, take another minute, pull in for question 2, and then we'll discuss it together. Okay, team, come on back. Go ahead and pull in for question 2 if you haven't already done so. We're looking for the carbon that is going to be the most electrophilic in character and characteristics of good electrophiles. Remember, it's going to be the one that has the most centralized positive charge associated with it. And really, it's all about what's associated or what's directly bound to that carbon. So I've got 4 choices here. 2 of them should be kind of easy ones out, like both C and D are kind of sitting in areas that don't really have anything that's going to pull electron density away to create a partially positive carbon. I would say the only 2 that you should be kind of like wavering about is A and B. And the correct answer looks like the majority of us are pulling in for answer choice A, and that is correct. What makes A a better electrophile compared to B? Well, it's the presence of the bromine, right? This is electronegative, so it's going to withdraw electron density away from this and create a partial positive charge here, whereas that bromine is pretty far away from B, and B doesn't really have anything else. Like, it does have a little bit of inductive effect with the, with the pi bond and with the, with the phenyl groups, the resonance kind of surrounding it, but it doesn't really have anything near as close as electron withdrawing as that bromine. Okay, so yeah, it doesn't really give us anything else, and A is really the only one that is close by to an electron withdrawing group. So as you guys all surmise, the correct answer here is A. Now, why is that important for you to identify the electrophile? Because that's going to be the site of attack. This is where all the action is going to happen. This is where the nucleophile is going to want to gravitate towards. So it's really important that you're able to identify at least those 2. Where's the electrophile? What's my nucleophile? Once you know those 2 pieces, then you can be able to predict at least the next step of that reaction. Yeah, David, absolutely. I think I'm a huge fan of drawing and making use of the scratch pad that you have access to on test day is huge, especially in the chemistry and the physics section. So don't hesitate to draw things out if you think that would be helpful. But I do want you to caution yourself from spending a bit much, like too much time on a question. On average, you should be spending about a minute per question. If you can see early on that a question is going to likely take you a bit longer, even if you know how to solve it, I encourage you to just move past it. Not because you can't do it, because you want to get rid of all the other questions that you know how to do quickly, and then you can just very much more at your leisure spend time on analyzing question nice and carefully with drawings, with calculation, with numbers, anything like that. Okay, our next learning objective, we're going to talk about a couple of different reaction conditions, including things like solvents and acidity, okay? So we've seen this drawing before. Some of the reaction conditions you see, you got methanol, you got an ether, you got acids. We'll talk about all of these components and why it's important to also identify these particular kinds of solvent. So I have 3 on screen here. We got acetic acid, water, and ammonia. What kind of solvents are these 3? What kind of solvents are all 3 of these? So acetic acid, water, ammonia. I mean, technically, I guess acetic acid can be 2 things, but. Oh, I was like, what kind of bear are you talking about? I get. There's like a meme that floats around about this one too. What do you think? What kind of solvent are these? They're polar, absolutely. Now, polar has 2 subtypes, like polar bear, but polar bears don't have 2 subtypes, but the solvent does. What kind of polar solvent is this? So important for you to be able to identify this, because this is going to be a really big clue when we get to the SN1, SN2s. How you're going to be able to tell apart one from the other, you're going to look at the solvent and also help see that. So what kind of solvent is this? Is this protic or aprotic? Definitely polar. All of those, protic, aprotic, are both polar solvents, but this one is specifically, so the prefix A means without, and protic is referring to the proton or the hydrogen. So here, all of these are going to be protic. Yeah, no, this is, but I want to make sure that we understand why exactly this is protic. It's not just because there's a hydrogen, but it's a certain kind of bond that is able to exist between molecules. Yeah, so Patrick's got it. It is a hydrogen bond. Now, who here thinks that this is a hydrogen bond? Anyone think that carbon attached to hydrogen is a hydrogen bond? Or I don't know. I can't think of any other examples. Oh yeah, like this. What do you think? Are these hydrogen bonds? I cannot believe how many times I've seen this confused on practice questions, that I want to make sure you guys all are walking away with knowing this. Not hydrogen bonds. So here's the thing. A presence of a hydrogen and a presence of, a couple of these others, the important key elements, does not make a hydrogen bond. In order for you to have a hydrogen bond, it's a type of intermolecular force. Intermolecular force meaning it's a type of interaction that exists between molecules and not within the molecule itself. So yeah, Patrick's right. You don't really want to call this a bond. It's more like bonds usually imply a sharing of electrons. Hydrogen bonds are more like hydrogen interactions. It's a really strong style type of dipole, actually. In order for you to have a hydrogen bond, you have to have a hydrogen attached to which of three elements? Which three elements you need? Not H bonds. In order for you to have a hydrogen bond, that hydrogen needs to be covalently bound to one of three important elements, not elephants. What do you think? You might think, Nikki's got it, that's right. So hydrogen bonds are fun, F-O-N. Fluorine, yeah, because it's organic chemistry, hydrofluoric acid isn't really an organic compound. So yeah, Patrick's right, it's mostly going to be between a nitrogen and an oxygen. So technically though, all three of those can form hydrogen bonds. So F-O-N. And notice these are all covalently bound, but the hydrogen bond is because of this pull. So the fluorine, oxygen, nitrogen will pull the electron density away from the hydrogen really, really well. So this is a huge partial positive charge. And this like dashed line I'm drawing here, that's the hydrogen bond, H bond, right here. Okay, so it's not the covalent bound, it's the fact that it exists, it sets up a dipole between that hydrogen and another electronegative element here. So this is the hydrogen bond here, okay? So anything that can set up a hydrogen bond is going to be what we call a polar protic solvent. So ammonia, water, acetic acid, alcohols, all good polar protic solvents. The reason why this is important to understand is it affects nucleophilicity. So if I was to ask about nucleophilicity within the halides, like purely on its own, like not considering any solvent, what's the most nucleophilic element on the periodic table? You're right, Nikki. You're right. What is the most nucleophilic element on the periodic table? So if I were to ask you periodic trends, so important on the MCAT, so this content session kind of touches upon a whole lot of chemistry. Fluorine, you got it. Fluorine is going to be our most electronegative element. But if I have a fluorine in a polar protic solvent, what's going to happen? Remember what I talked about? Wedding crashers, stage 5 clingers. What's going to happen if I throw in a fluorine anion in a polar protic solvent? So important. This understanding, it took me forever to get this to stick, but repetition really helped. What happens to fluorine in a polar protic solvent? Does it act as a nucleophile? Is it going to go donate its electrons to another carbon atom? If I have that in solution in a polar protic solvent, it's going to deprotonate the solvent. That's right. So the reason why this is important is because the type of solvent will affect the nucleophilicity of your reagent. So the strongest out of these halogens, the strongest of the four is going to be which one? Which one's the strongest nucleophile in a polar protic solvent? If you think about this, its ability to pull the protons off, warring with its ability to go attack a carbon, it's going to be dependent on its, you know, its basicity, I guess, more than anything else. So here, nucleophilicity will decrease as you go down the periodic table. Even though technically fluorine is going to be the most nucleophilic overall in a polar protic solvent, because it's going to deprotonate the solvent, the most nucleophilic is actually going to be iodine. And exactly, David. So this is the most nucleophilic in a polar protic solvent. It's going to, everything else is going to want to pull the protons and act more like a base instead. Yeah. Yeah, it could be bromine, but even better than bromine is going to be iodine because it's just, it's bigger. Okay. Super important there. So we talked about polar protic solvents, and I'll tie this in later on when we talk about SN1, SN2. So here's just a quick little drawing to show you that, yeah, so you can like pull protons. This is happy. This definitely wants to happen. This does not. Hydrobromic acid is very much going to want to donate its protons. So this is, yeah. So instead, what's going to happen? What would we call this kind of drawing? The way I've drawn it here. Yeah, Tara, I can repeat it in just a bit. What do we call this? When I've got a water kind of surrounding an atom like this, what do we call that? I'm trying to think of what I said, Tara, so I can repeat it. I think I said something about bases. Fluorine is a better base. It's going to want to pull a proton instead of act as a nucleophile. Nucleophiles are ones that are going to go and donate their electrons to like a carbon. It's going to act as a nucleophile. But in a polar protic solvent, it can't do that because instead it's going to pull a proton off the solvent. And so nucleophilicity will always be better with the most, the furthest down the periodic table. Yeah. So it would rather act as a base instead, Tara. Fluoride is going to be, the fluorine atom, like anion, is going to, instead of acting as a nucleophile, it'll act as a base instead. Exactly, David. That's right. This is a solvation, like a shell of water around it. So it's going to get solvated. Bromine's happy to then still attack and act as a nucleophile instead. So this is what you'd prefer to do. You'd want to have a good nucleophile that has a nice solid negative charge on it, but it's not going to pull a proton off instead. It's going to be solvated by the water. Yeah, hydration, solvation, shell, something like that. That's exactly it. Okay. Let's talk about the other one here. Yeah, we got that already. So these are polar aprotic. A meaning that prefix A meanings without. So it doesn't have the hydrogen bond capability. So just to be clear, acetone. Can acetone form a hydrogen bond? It's got an oxygen, it's got a hydrogen in it, but can it form a hydrogen bond? Or even ethers, or any other type of ketone, or even an aldehyde. That's another good example, aldehydes. Can any of those form hydrogen bonds? So if you want, you can draw it out to show you that, like an aldehyde looks like this. Any other ketone, an ether, right? Maybe it's got a hydrogen here. Free time. It can act as a hydrogen bond acceptor, if that's what you're referring to, Dave, you're right. But it itself cannot be a hydrogen bond donor. It can't form a hydrogen bond with itself. You got it. Henry's not really crazy. Henry is very busy. Henry's taking his step exams next week. He has 0 free time, except to hang out with us. Okay, so yeah, so what would be good about this with regards to nucleophilicity? Well, if it doesn't have the ability to donate free protons, that's good news, because then what will it do? Which one's the strongest nucleophile in a polar aprotic solvent then? Which one's going to be the strongest nucleophile in a polar aprotic solvent? Well, I say so, Patrick, and therefore it must be true. Out of the 4 I've got drawn, Which one is the strongest nucleophile? So in polar protic solvents, we said that iodine was the strongest nucleophile. In polar aprotic solvent, it's going to be fluorine. You got it. Now, is it likely that fluorine's going to hang out? Remember, being stage 5 clinger? Not likely. Probably the next best bet is going to be chlorine. But yeah, absolutely. It increases up the periodic table within a group here. But yeah, it's going to be the fluorine. It's going to be the best nucleophile because it is. It is the best nucleophile overall. And polar aprotic solvents are not going to hinder it from acting as a nucleophile. It's not going to, be able to steal protons away. Okay, how about these? Benzene, toluene, hexane. What kind of solvents are these ones? What kind of solvents do we have here? Not all that likely to show up in certain kinds of orbital reactions on the MCAT. And there's a specific reason why. What kind of solvents are these? I'll tell you where you might see them. Mostly in the context of a technique. Yeah, Nikki, they're non-polar. Benzene, toluene, hexane. Very, very, doesn't have a molecular dipole whatsoever. So yeah, where you would see these, not with carbonyl chemistry, right? Like this is not going to want to hang out with anything that is going to be polar. So yeah, charged nucleophiles are not going to dissolve. You're not really going to have a good electrophile in them because they're not going to be able to be soluble in them. So like dissolves like is really important to kind of keep that in mind. You're not going to have nucleophiles and electrophiles in nonpolar solvent. When would you see these? Certain kinds of chromatography and separation techniques is probably the only thing I would think of if I were to consider these kinds of solvents, but not in the context of most organic chemistry reactions, okay? So let's talk a little bit more about what we touched upon a little bit earlier with Lewis acids and bases. So definition-wise, Lewis acids. The way I always kind of remember these, because remember you got the Lewis, you got the Arrhenius, you got the Bronsted. I always think Lewis, electrons. So is my mnemonic to help me remember that this is all about the movement of electrons, and acids, the AA is an acceptor. So a Lewis acid is an electron acceptor. That means the base must be an electron donor, okay? So these are all about the movement of electrons. So here we have tetrahydrofuran. It is one way to describe this would be as a polar aprotic solvent because it is polar, but it doesn't have a proton on there. But it is got these lone pairs. So what do you think? Can it act as either a Lewis acid or a base? Or if so, which one? Which one? Is it a Lewis acid or a Lewis base? Given the presence of lone pairs on those oxygens. So if I think, is it going to grab another set of electrons, or is it going to want to share possibly those electrons? Well, since it has those electrons available, right, Lewis bases are going to be probably what you're thinking here, right? So Lewis bases are the ones that are going to donate or share those electrons. Yeah, it's definitely a Lewis base, Nikki, absolutely. What can it donate to? Well, something that's going to want to grab those electrons. Borane is a weird example. We don't usually see this because it's not organic, but borane is boron with 3 hydrogens associated with it. It's a strange one because it's like the one just before carbon. So it doesn't have a full octet there. So it's got an unfilled shell that it could be happily grabbing. So see what we get here. We get a type of bond. What do we call this kind of bond here? Agreed, Patrick. What do we call this kind of bond? It's got a special name. There's like an old school name for it as well. I don't usually see the old school name that often. So this is often, well, Lewis acids and bases, when they do, it's a special kind of covalent bond. Covalent just means shared, right? I'm sharing the electrons between the oxygen and the boron, but the kind of covalent bond is called coordinate. Also known, old school style, as dative. So dative or coordinate covalent bonds. What this means is that the electrons, both the electrons that are within that bond, that covalent bond, are coming from the same atom. Yeah, exactly. Tara, you got it. So it's not a Zwitter ion. This is, but I can see why you'd think that, David, because it's got the plus and the minus. Yeah, it's not really a Zwitter ion. I can see why you'd think that, but the reason why it is the way it is because it's given up its electrons to the bond itself. I don't know if I'd really say that this has charges on them, to be clear. I think it's more like it's shared between the two atoms. No. So David, I don't know if it's necessarily that you're wrong. With the way it's drawn, I would say technically, yeah, you could call that a Zwitter ion, but I just think that these charges don't really exist in this molecule. So it's the electrons are shared, but it's all coming just from the oxygen itself. The boron doesn't have any electrons to give up. It's going to take it, but it's all coming from one place. Okay, so yeah, so it's a coordinate covalent bond, and that's a formative, like a really important thing. When you have a Lewis acid base pair, so you've got a Lewis acid and it's accepted the protons, the kind of bond it's going to form is going to always be a coordinate covalent bond. Now, why am I doing this? Why do I care? What would be another way to call something that's going to donate electrons? I just spent like an hour describing this kind of reaction. What is another name for an electron donor? Think about the players we just described. The reason why we're doing this is so that you don't recognize, like you recognize that this is something you already know. What do you think? This is so important. What is something we just described that would want to give up electrons? It's got plenty to give away. It's got a lot of negative charge associated with it. It's a nucleophile. That's right. This is a nucleophile. So important. A Lewis base is a nucleophile. It's a proton acceptor. It could be a base. Yeah, you're right. Technically, Bronsted-Lowry bases are also Lewis bases as well, but in the context of organic reactions, this is a nucleophile. That makes an electron acceptor, the site of, wanting to have more electrons around, this is an electrophile. Same thing. These are not different concepts at all. The reason why we talk about Lewis acids and bases is not because this is an acid-based lesson, it's because these are the same principles, okay? If we were to kind of, discuss a little bit more about other reaction conditions, we could talk about the other forms of acids and bases. So here we've got an acetic acid, technically also a Lewis, base. It can donate electrons, but in the form of this time, it's going to be a hydrogen. So this is more, in the context of specificity, this would be like a Bronsted acid here. So it's going to donate the protons. Where is it going to donate? Something that's got some, things to accept, right? So pyridine is usually used as a solvent here, but it can also act as a Bronsted base. You can grab that proton, be positively charged, and it's happy. Acetic acid is something that is a weak acid, but generally not so bad about giving away its proton. So these are other reaction conditions to consider here. Okay, so let's very briefly describe acid-base strength, and then we're going to kind of like wrap it up for the end here. So out of the what is this, 6 molecules that I have described here, which one's the strongest acid? And I'll bring back another key principle that we described at the very beginning. What is the strongest acid? Is it methane on the left, and they are ordered in a particular sequence here for a reason, or is it hydronium ion on the right? Where is the strongest set of acids in this range of molecules? So acidity is all about, same idea, the stability of what the product is. So a strong acid is one that's going to be happy to give up its proton and form the conjugate base afterwards. So yeah, absolutely, David. Hydronium is going to be the strongest acid. If I were to plot the pKa's of all of these, you'll see that this is it's got a negative pKa, actually. It's very, very close to 1. Hydronium has a ability, it's actually the strongest acid that exists in solution. Anything that is stronger than hydronium is going to give up this proton to water and form more hydronium. So This is the range, and the reason why is because it can happily give up its proton, actually not that direction. The proton can leave, where we go, come on, there we go. The proton can take off, right? And then it's gonna form water, and water is very happy on its own. So the stability of the product is gonna dictate the strength of the acid or the base, really. So these are all very strong acids on the right, terrible acids on the left, right? And you can also be able to, once you have the pKa, you can figure out like, you know, the pKb if you wanted to. For instance, you know, if I have a pKa of 4, I would be able to know that the pKa of the conjugate base of acetate is going to be 10, right? So yeah. So think about the stability of the conjugate base. Here are all a bunch of bases. These are all the conjugate bases of what was left over after it donated the proton. The strongest base is going to be the weakest acid. They are going to be opposites to each other. So which one's the strongest base? It's going to be this guy. This guy hates being like this. It would much rather grab a proton and make itself, you know, an alkyl group again. So you can see that the strength of the base is going to be same sort of pattern. It's all about the stability of the product itself. So if it's going to grab the proton and be happy, the one on the left is going to be the most basic out of all of them. Okay, got another set of questions here. Yeah, I will do this one, and then we'll like wrap it up for the last part. So take a minute to do question 3, and then I'll give you a little bit of a hint afterwards about Roman numerals. So take 1 minute, do this question on your own. Okay, come on back. Go ahead and pull in if you haven't already done so. Here is a tip for you. Roman numerals, despite what you might think, aren't actually that common. I had this discussion with a, you know, one of the folks working on our team with making, you know, a lot of our practice tests, and he sat there and actually he counted. He counted how many Roman numerals appeared on the AMC full length. And he said that on average, it's like 1 per section, 4 per exam. That's how many Roman numerals there are. We tend to overinflate the importance of these. So I'm going to give you a tip on how to work through them, but I also don't want you to stress over them because they're not all that frequent per section. So here's how I would do it. I want you to pick the Roman numeral that appears just twice. So out of the 3 Roman numerals, you want to look at your answer choices and think which one just appears twice. You can pick Roman numeral 2 or 3. Now, why? Well, by analyzing one Roman numeral, you can bring it down to a 50-50. If you were in a rush, you pick between those 2 and you move on. And that way you do the least amount of work to get to the correct answer. It's also much more likely that you're not going to have to analyze every single Roman numeral. So let's do that. Out of the 3 Roman numerals, it looks like Roman numeral 2 and 3 appear twice. So I'm just going to pick Roman numeral 2. Roman numeral 2, let's talk about this. Is this a Lewis acid? So what's the definition of a Lewis acid? Remember I said a little bit earlier, electron acceptor. So we're looking for something that's going to accept an electron. Ammonia having, you know, this, right? This is an ammonia, it's got some lone pairs on it. Is it going to grab another electron? No, I mean, if you think about If you think about ammonia and how it functions and like, even amino acid chemistry, it's the one that's not going to, accept electrons. It's usually going to be donating electrons. So just based on that alone, if you know that ammonia is not going to be a loose acid, you can get rid of Roman numeral 2 and Roman numeral answer choice B and D. So get rid of anything with Roman numeral 2 and look at what we're left with. So my question to you is, which Roman numeral do we want to look at now? Because one of these is going to be true regardless of what you do. Which Roman numeral do we want to look at now in order to get to our correct answer? So I'm all about efficiency on the MCAT. You don't get extra points for doing all the work. You get the points just for the correct one. Doesn't matter how you get to that correct answer. So it's not cheating. Which Roman numeral do I want to look at now that I've eliminated answer choice B and D? Yeah, let's look at Roman numeral 3. BF3, trifluoroboron. So we have seen a version of this. We saw borane, which is BH3, but it doesn't really matter. Regardless of whether it's hydrogen or it's fluorine, it's our prototypical example of a Lewis acid. It's the one that's going to grab because boron's got all that extra space to grab an electron. So yeah, it's got that classic Lewis acid style structure. C is our correct answer. Notice I didn't even spend any time on analyzing this guy and why it's a Lewis acid. Don't bother. On test day, you don't spend time on analyzing answer choices you know to be wrong or right. It's not cheating at all. But in your review, it's important to kind of do that work. Why is Roman numeral 1 a Lewis acid? What is that? CH3CHO. At first, I thought this was a typo, and I thought it was missing a negative sign. But then I was like, no, it's written right. What do you think? CH3CHO is written like that on a reason because it is acetaldehyde, right? So it's an aldehyde. It can accept electron pairs. It's the site, right? It's an electrophile, which is a good Lewis acid. So this is something that's going to accept electrons, hence why it's correct. Yeah, acetaldehyde, you got it, that's right. So carbonyl chemistry, remember we talked about electrophiles, how they are all going to be good Lewis acids as well. So hence why Roman numeral 1 is correct. So this was a tough one, but I want you to understand the principles behind this, that Lewis acids and bases are the same thing as a nucleophile electrophile discussion that we just had, okay? So let's kind of work on our next learning objective and talk about chemoselectivity. So this is a very brief discussion here. Yeah, boron's like one of those ones that just doesn't follow all the rules. It only has, it's like the fourth, 1, 2, this is the third, right? No, 1, 2, 3, yeah. So just after it is carbon. So it is weird in that it can form 3 bonds happily, but it's got more space so that it can grab more electrons. Yeah, it's fine. It's one of those weird ones that doesn't follow all the rules. It's too small to care. I mean, that's pretty much it, yeah. I'm not going to spend a lot of time on the chemoselectivity component just because this kind of touches upon other types of organic reactions that we're not really going to have time to spend on today, but I'm going to briefly describe them. Chemoselectivity is all about the idea behind things like protecting groups or steric hindrance. So here, if I got propane 2-dione, I've got this the setup here. What is this? If I've got 2 carbonyls with a carbon kind of flanking it, what do you think? What might I be probably referring to next? It forms kind of I don't want to give it away. But what do you think? What do you think is going to happen? What's so special about maybe one of these hydrogens that's in the middle here? There's a special term for this kind of reaction, and it's due to the fact that you've got a carbonyl and a carbonyl kind of flanking this one carbon in the middle. So if you think about this, well, I've got partial positive charge, partial negative charge here on both sides. Yeah, it is extra acidic. That's right. So now carbon, hydrogens, they don't really want to give up their protons. So it's not like this is a super acid at all, but it's more acidic than you would normally expect for a carbon. So yeah, so this process is that this carbonyl carbon can be a good electrophile, right? This base can extract that hydrogen, so it's a little bit more acidic than normal. And what happens is I get a little bit of rearrangement here, and I form this thing. So if I were to, I don't know, protonate this, what do I call this molecule? It's got a double bond, so like an ene, and it's got a hydroxy, which has got the suffix -al. So what kind of molecule have I formed here because I have an acidic hydrogen? And then there's a whole name for this. The reason why this is important is because this will give you an idea of where this reaction is going to occur. It will give you a kind of compound that could show up on test day. It's not super, super high yield, but it's important to know. So if I think about the name, ene, right? And then all, that's right. Yeah, this is an enol. This is a type of reaction called a tautomerization. So I can get a little bit of resonance to stabilize, and the fact that I now have this, what does this now create? A negative charge on a carbon, which is unusual. You don't usually see negative charges on carbons, but this is an absolutely fantastic nucleophile. This enolate is a really, really good nucleophile, and that only happens because I have a slightly more acidic hydrogen in the presence of a base. So this is an enol, okay? So some form of kenol selectivity here, just because of the way that this molecule is set up. You got some steric protection here. If I've got a carbon that is, got a couple of methyl groups and a bromine versus this one of them is going to be a little bit more likely to react just due to sterics alone, right? This is a quaternary carbon. It's sterically hindered. It means that there's something physically blocking its way. This one doesn't have steric hindrance really. It can be easy to attack. Now, here's the thing. Is that always true? No. It depends on the kind of reaction this is, right? If this was an SN1 reaction, which one is going to be the one that's reacting? And then I'll describe a little bit more about SN1 and SN2. Is it the red one or the blue one? If I was an SN1 reaction, is it the red carbon or the blue carbon that's going to be the site of the reaction? SN1 is all about the carbocation, if you don't quite remember. So carbocations, they need their buddies, they need their friends to support this very, very unstable positive charge on the carbon. So which one has got the most amount of friends around it? If you're thinking that red carbon, you were correct. So this is, even though it is more sterically hindered, it's not a big deal because this bromine leaves first. This is going to be an SN2 style reaction because sterics matter in SN2. Okay, so let's talk about that in a little bit more detail actually in just a second. The last bit of steric protection has to do with protecting groups. This is all about the idea that, both of these are carbonyls, both of them technically can react to whatever I've got here. I can choose to only react one of them by using, this is a diol here. And if I protect one of the group with the diol and then I extract it, right, I can essentially reduce this one of these compounds and not the other, and then I can pull off that weird alien looking guy with some acid. And now I've just reacted this carbonyl over here and not this one. So that's it. So in like other sessions, we do talk a little bit about this in other contexts. For this one, I just want you to understand protecting groups can select for where your reaction is going to occur. Okay. The last bit is the lead up to all of this. We're going to talk about SN1, SN2 reactions in this last one. Before I do, though, there's one key point here. What's the difference between SN1, SN2 reactions, and then nucleophilic acyl substitution reactions? What is the difference between these two? I knew what both of these were, but I don't think it didn't occur to me until way later that these are two separate types of reactions. And I think it's important to distinguish between them. What's the difference between these two? Both of them involve nucleophiles. Like SN1 stands for substitution nucleophilic. But even though both of them have nucleophiles and both of them have electrophiles, it's really the electrophile that's the difference between these two. So what is it? What's the difference between SN1, SN2 reactions versus nucleophilic acyl subreactions? Both of them are substitutions, both of them involve nucleophiles, but it's the electrophile that matters here. So if you know what acyl means, acyl is a carbonyl. So this is sp2 hybridized. Whereas SN1, SN2 reactions, that's right, Patrick, you got it. This is about a carbon that has 4 bonds, and this is sp3. So if you ever are in the situation where you're like, I know both of these, but I don't know which one is the one to call this kind of reaction, look at the hybridization of your electrophile. If you know that's sp3, that's going to be an SN1, SN2. If it is a carbonyl carbon, that's a nucleophilic acyl sub, and that like encompasses a huge proportion of most of the MCAT orgo that you're going to see on test day. Like in your orgo class, you're going to do way more. This is mostly the scope of the majority of the reactions. It's not to say it's complete, but this will be the bulk of it for sure. Possibly, Patrick, I might recognize you. So yeah, none of these over here actually talks about SN1, SN2. So let's kind of move fast forward over here. Key characteristics of SN2 reaction. First of all, tell me, what does the 2 refer to? What does the 2 mean? SN1, SN2. They differ by this number. So what do you think that means? What does the 2 refer to? I'll give you a hint. It has to do with the rate of the reaction. So if you bring in a little bit of kinetics here, kinetics meaning how fast does the reaction occur, chemical kinetics involve the components of the reaction in the rate limiting step. So that's my big hint. Why is there a 2 in SN2? 2 steps? Oh, no, actually, it's the other way around. And Tara, I get it. I thought that's what it was. I thought the 2 meant 2 steps. I know, I hear you, I hear you. I got this backwards for so long. It's actually 1 step and it's the other way around, but the 2 is all about what's involved in the rate limiting step. So it's a bimolecular nucleophilic substitution reaction. It is 1 step, and it's because both of these, the concentration of both of these things, 2 things have to be involved in, and that will affect the rate, right? So if you vary the concentration of this one or this one, it's going to change the rate of the reaction because this is the rate limiting step here. Bimolecular meaning 2 molecules involved, okay? So the way SN2 reactions work is that in 1 concerted step, so this is the 1-step component of this, the nucleophile is going to attack the electrophile. Now, the reason why you can't have a lot of sterics here is because it happens in one go. If you've got a lot of bulky groups around it, it's going to hinder that nucleophile from attacking at the same time our leaving group is going to leave. Now, here's some fancy animations here. Take a look. Ooh. So then you can see that you've got a transition state at some point. So here's our transition state. Carbon doesn't really have like 5 bonds here, but it's trying to show you that the nucleophile is coming in at the same time that electrophile, the leaving group is leaving. So here, a key component to SN2 reactions is the kind of product it makes. Tell me about the product here. Tell me about the product here compared to what we started with. What is a key characteristic, especially if you've got, actually only if you've got a chiral carbon? What's so important about the way the reaction is happening or the way the attack is happening and the way the leaving group leaves? So the way it leaves will always show you physical inversion. By that I mean, it's going to be like an umbrella flip, right? Umbrella, like I've got it over my head, it's going down. If I, have a strong wind, it's going to flip it completely up in the opposite direction. It will always give you a physical inversion. Now, is that going to always give you an inverted stereochemistry? No. It depends on the priority of the nucleophile versus the leaving group. If these are both first priority, then yeah, I'm going to get an inversion of the stereochemistry. But it's not always true, to be clear. If they don't have the same kind of priority, you may or may not get an inversion. So it's important that you redo the whole RS configuration once you do one of these reactions, because it's not always the case that you're going to get an inversion. So that's really important to kind of keep that in mind. And I've seen traps on that kind of question before. So key thing here is all about the sterics. So if you've got a lot of steric issues with your electrophile, then it's going to hinder the reaction. So the barrier here, maybe I'll write it down here. Barrier is sterics. What kind of solvent would you want in an SN2 reaction? You will want a polar. I don't know what is going on with this. It looks terrible. You want a polar aprotic. Why is that the case? Well, the strength of the nucleophile is really important. If I want to maximize the strength of my nucleophile, I don't want protons around, glomming onto the nucleophile and then it acting as a base instead. I'd rather save its negative charge to be able to attack it. Okay, so polar aprotic, really, really important here. I don't want to have protons floating around with my nucleophile, so I want to save that nucleophile and its strength, because that's really the key characteristic, is I want a really strong nucleophile. Okay, so that's SN2 reactions. Let's take a look at our last one for SN1. The way I always remember this, and this is so cheesy, but it works. SN1 has a 1. If I add another line to this, I form a plus, and that reminds me about the carbocation. Okay, so unimolecular, the 1 involves one thing in the rate determining step. It does involve 2 steps here, but it's first order, meaning that the concentration of our electrophile alone, not the nucleophile, is what's going to determine the rate of the reaction. Why? Because the first step involves you forming the carbocation. So notice my leaving group leaves all on its own. All on its own. Nothing is forcing it off like the nucleophile in our SN2 reaction. Now, the kind of solvent I want is polar aprotic. Why? Because then that hydrogen can hang out with this and make it happy. So it's going to stabilize the leaving group all around. So it's not going to to be clear, this is more like a solvation shell. It's not like it's donating the protons and reforming hydrobromic acid, but it's going to stabilize that leaving group and allow for this kind of stable carbocation. So the stability of the carbocation is all dependent, like I mentioned a little bit earlier, on its friend. So notice that this is a tertiary carbon. So it's got 3 carbon friends. They are all electron donating. So it's going to stabilize. It's going to donate electrons to the positive charge and make the carbocation about as happy as it possibly can be. So that's really important there. The next step is really fast. Your nucleophile is going to come on, right? And it's going to attack. This is sp2 hybridized at this point because it only has 3 bonds here. And I'm going to show you another fun little animations. You'll see that the nucleophile, since it's sp2, it's planar. So it can attack from the top or from the bottom. And because of that, the products are going to be a mix of 2 stereochemistries. I'm going to have a racemic mixture so that the nucleophile can be projecting one way or the other, and it's going to be at a one-to-one rate here. So racemic meaning it's not going to be optically active. So here, like the barrier is not sterics here, but it's about the cation stability. What makes carbocation stability? It's its friends. If it has good friends around, it's going to be able to be stable and the reaction is going to be able to proceed. The type of nucleophile you can have doesn't matter, right? You can have weak, strong, it doesn't matter because the reaction proceeding is all due to the carbocation formation. The type of solvent you want is going to be polar aprotic to be able to solvate that leaving group after it's done, okay? Patrick's making fun of my penmanship, and I'm going to blame my tablet, and it's not me. I swear my penmanship is usually much better than this. Okay, so hopefully that gives you a better sense of why it's important to consider all of these, knowing the nucleophile, knowing your electrophile, understanding SN1, SN2 reactions, key component on the MCAT, really, really important. I'm going to go ahead and skip this question, but we are technically at time, but I got one last question to do, and I'll stay on camera for it. 1 second here. Let's walk through this last question together, team. So which of the following reactants is most suitable for an SN2 reaction? So I've got 4 molecules here. Tell me, team, tell me, SN2 reactions, what kind of carbon do I want? What's really important for SN2 reactions? It's going to wrap it up for the end. I know I did a lot of talking in the last bit of this, so I want to hear from you. What do you want to keep an eye out for SN2 reactions? SN2 is not the carbocation one, remember, right? So this is the one that's got the attack of the nucleophile the same time the leaving group is going to take off. So what do you think? Throw your answers into the chat. I would love to hear from you. I've got a chloromethane, I've got 1, 2, 3, like a propane, I've got an isochloro thing, I've got a quaternary one. These all differ on the type of carbon this is attached to. So this is a methyl, this is primary, this is secondary, this is tertiary. What is the determining factor for an SN2 reaction? It's all about sterics, right? So if you understand that the sterics is most important, if you have something that is sterically hindered, your electrophile is hiding behind a bunch of other stuff, it's not going to happen. The reaction that's going to be most suitable here is answer choice A. Our methyl chloromethane is going to be the most suitable reaction for SN2 because it has the least amount of sterics associated with it. And that is it for us, team. So I'm going to just like go ahead and take us to our final slide here. So in review, understand the main players. We talked a lot about nucleophiles, electrophiles, components of good leaving groups. We discussed briefly some of the reaction conditions and what makes good acids and bases and how they affect the reactivity of compounds. We talked about Lewis acids and bases, how it's really the same thing as nucleophiles and electrophiles. We talked briefly about chemoselectivity, and then we wrapped up the night with SN2 and SN1 reactions. Remember that last bit. I think the most important out of what we described here is the very first part of our discussion and this last part here. So keep that in mind. MCAT specific wise, SN2, SN1, you got to know what determines what. And that's it for us today. So I'll stick around. If we have any questions, please do feel free to ask. But other than that, I want you guys all to have a great night. Good luck on your MCAT journey. And I do hope you join us for more sessions like this in the future. And that's it for us. So have a good night, and I'll see you in the future.